Hi, George Diamond here. Welcome to our flipped classroom. This is our next lesson. Now today we're going to take a look at and learn about derivatives of the natural exponential function. Now in our textbook, this is section 5.4. Now in our next video, we're going to look at how to find the antiderivatives and integrals of the natural exponential function. But today we'll take a look at derivatives of exponential functions. So to get started, the natural exponential function is y equals e to the x. Now, this is our parent function. The parent function, of course, just like any other function, it can undergo different types of translations, transformations. You can shift it up or down, left or right. You can see the graph of y equals e to the x. This is actually a sketch of the graph, something like this. You can see it. It'll approach the x-axis going to the left, and then it increases upwards going to the right. All right, so once again, y equals e to the x. This is our natural exponential function, or f of x equals e to the x, if you will. One thing to remember, one very important thing to remember about y equals e to the x. Right? This is the inverse of the natural logarithmic function. Now, in our last video, we looked at how to find the derivatives and integrals of the natural logarithmic function. But y equals e to the x and y equals natural log x are inverses of each other. So those are inverses. Right? So those are inverses. So y is equal to e to the x, and that's only if and only if x equals natural log y. Right? So this is true if and only if this is true. So y equals e to the x. So these are inverses. So once again, y equals e to the x, the natural exponential function will always be the inverse. Is the inverse of the natural logarithmic function. So those are inverses. Now, if you look at the graph over here, so I've already got the little sketch of the graph. It's not a real precise graph, it's just a sketch. You can see the graph. As we go to the left on our graph, the graph gets closer and closer to the x-axis. That makes the x-axis a horizontal asymptote. So the curve will never touch the x-axis. It just keeps getting closer and closer and closer. It crosses the y-axis here at positive 1. Also, now a couple properties I want to talk about. So several properties. We looked at the same type of properties with the natural logarithmic function earlier. But a couple properties that we want to look at here of y equals e to the x. So e to the x there. So a couple properties. Okay, first the domain. Now the domain of the natural logarithmic function is negative infinity to positive infinity. Here the domain is x, and it's very apparent as you look at your graph here. Okay, the graph goes to the negative infinity. It'll just keep going to the left, and it'll just keep going to the right. So the entire x-axis, x values along the x-axis of our graph would be used in the natural exponential function. So the domain, that is the x values, would be negative infinity to positive infinity. Whereas the range, if you look at the graph here, the graph will never go below the x-axis. So the range is your y values, right? So from the graph here, you can tell that only the y values from 0 up are used. That's all. Y values below 0 are not used. Also, 0 is not part of the range. So we can say the range would be from 0 greater than or equal to 0 to positive infinity. Okay, also a couple more things I want you to notice about the natural exponential function. Okay, the next property, if you will, is that the curve is continuous everywhere. So there's no jumps or gaps. Right? So no jumps or gaps. So it's going to be continuous everywhere on the graph. Okay. Also, the graph is going to be the graph will be increasing everywhere. So it's increasing everywhere. Now remember, if you remember now, the first derivative tells you whether or not a graph is increasing or decreasing or not. So where y equals e to the x is increasing everywhere, that means that the first derivative will always be positive. So you can imagine if you could draw a tangent line anywhere on this curve, right? So a tangent line anywhere on this curve, you would have a positive slope. So since the curve is increasing everywhere, then the first derivative would be positive everywhere on the graph of the natural logarithmic function. And the graph is 1 to 1. So the function will be 1 to 1. Okay, also, so you look at the curve here, our sketch, right? So it's obvious that the curve is concave upwards everywhere. Right? So it says increasing everywhere, and it's going to be concave upwards everywhere. Now, if you remember, The second derivative describes the concavity. So the second derivative describes the concavity. So since it's concave upwards everywhere, that would tell us, or that would indicate, that the second derivative is going to be greater than 0 everywhere. So the second derivative would also be positive, right? Since it's concave upwards everywhere, the second derivative is going to be positive everywhere. So the first derivative is positive everywhere, second derivative will be positive everywhere also. Okay, also, the limit. So the limit as x approaches negative infinity of the natural exponential function is 0. Right, now, if you look, if you can imagine on the x-axis here, okay, if we're going to the left, right, so if you pick out a point on the x-axis here, come up to the y-axis and over, that puts us right here on the y-axis. As you come closer, that puts us about right here, here, and you can see as we go further and further to the left, okay, the corresponding y value gets closer and closer to 0. So the further you go to the left here, the closer that you would get to the y to 0. So we see the limit as x approaches negative infinity is 0. Even though, y technically it won't ever get to 0, but the limit though as x approaches negative infinity would be 0. It just gets closer and closer to 0. So that makes it a horizontal asymptote. Also, the limit as x approaches positive infinity, e to the x is positive infinity. So as you go to the left, right, the y value goes straight up. Right? So as x goes to the right, as x goes to the right, your y value goes up. Right? So we say that the limit as x approaches positive infinity is positive infinity. Right. Now also, let's go and take a look at the graph of y equals natural log x. I said these are going to be the y equals e to the x, so your natural exponential function and the natural logarithmic function should be inverses. So if you look at the graph, it's going to be symmetric with the line of y equals x. So let me take a look at our graph here and plot a couple points here. So like so, this is the graph of y equals x. Right? So if it's an inverse, it's going to be symmetric with respect to that line, right? So if the point 0, 1 is on the graph of y equals e to the x, then 1, 0, so this here's 0, 1 here, then there should be a point at 1, 0 on its reciprocal. So if you look at the reciprocal, this would be y equals natural log x. Will look something like that. So it's going to, with the natural logarithmic function, it's going to approach your horizontal axis, or the y-axis will be a horizontal asymptote, will be a vertical asymptote, right, for y equals natural log x. So if you look at the, it's inverse, the graphs of the two inverses, they will be symmetric with respect to the line y equals x. Okay, so just a couple properties. Your domain, negative infinity to positive infinity, the range is 0 to infinity. The graph of y equals e to the x is continuous, increasing, first derivative positive, and it's 1 to 1. It'll be concave upwards, second derivative is positive. The limit as x approaches negative infinity is 0, and the limit as x approaches positive infinity is positive infinity. So just a couple properties there you want to kind of keep in mind as we look at some of these functions. So let's see if we can solve, let's start off with, see if we can solve some equations. So when we work with derivatives and integrals of natural log, the natural logarithmic functions here, these e functions, you have to be able to solve log equations and exponential equations with e in them. So let's take a look at a couple of those. So let's see if we can solve a couple of equations. So let's get this erased here. Here we go. Okay, there we go. You about got it? All right. Now, before we actually get into an equation, a couple of relationships that you need to remember. These are called inverse relationships. So inverse relationships. Now, involving natural log. Now, I think my students have already seen these relationships, but I want to kind of touch on them again as we get started looking at just a couple of equations here. Okay, first, natural log e to the x is equal to x. So if you were to see an expression like natural log e to the 3x squared, right? This is simply 3x squared. You can drop the natural log e and you just bring that exponent down. All right? So that's the first. Okay, the second one is e natural log x is also equal to x. So if you have e natural log, you can drop the e natural log as simply x. So a couple of important relationships there as we look at some of these e equations, these exponential equations, and some log equations. Okay, we kind of run into this sometimes, so you got to watch out, especially the first one we use quite a bit. So let's take a look at, I guess not really calculus, I guess it's more pre-calculus. This is a little review from pre-calculus, so a lot of you may already know this, and we actually looked at some of these examples in one of my previous videos, but I'm going to look at just a couple of them here. Okay, let's see if we can solve a couple of these equations. So solve each equation. So a couple of equations. Here's our first problem. Okay, let's do 7 equals e to the, so do 7 equals e to the x plus 1 power. Okay, let's try this e equation, if you will, this exponential equation. An exponential equation, you'll see the exponent in you see the variable rather will be in the exponent of your e here. All right, so as we get started, to get x out of an exponent, it takes a logarithm. So you have to use your product property, so your power property, to get x out of the exponent. So we use the power property. So what we're going to do is we're going to take this is an e, so we're going to take the natural log of both sides. We do natural log 7 equals natural log e to the x plus 1. Now, keep in mind, you can use any logarithm you want. So if you want to, you can use log, you can use common logs, you can use base 3 logs, you can actually use, you can take the logarithm of both sides of your equal sign here to solve. Now, since this is an exponential, an e function, right, so it's probably a lot easier, a lot better to use natural logs. That way we can use our inverse relationships as we solve some of these equations. So as we solve this now, this gives us natural log 7 equals, now natural log e to the x plus 1, we're going to use this property right here, is simply equal to x plus 1. All right. And to solve this for x will give us negative 1 plus natural log 7 equals x. And that's going to be our solution. Now for you, the decimal answer, when I did it, I got 0.946, approximately 0.946 equals x. So you can check that on your calculator and make sure that the approximation is correct. Okay, let's try another example. We're going to do about 5 equations here. Let's try another one. All right, so number 2. Okay, let's try this exponential equation. Let's do 100e to the, so 100, so let's see, 100e. So 100e to the negative 2x minus 5. So minus 5 is equal to, and I'm going to go ahead and erase these. So minus 5 equals 30. Okay, let's try this problem here. Let's try one where we're going to have to simplify it a little bit before we can take the natural log of both sides. Okay, you can't take the natural log of both sides of your equal sign until you get e to the negative 2x by itself. So we need to isolate e to the negative 2x. So we'll start off, let's add 5 to both sides here. It gives me 100 e to the negative 2x equals 35. So 35. Now let's divide both sides by 100. Okay, that gives me e to the negative 2x equals, now 35 over 100 will simplify to 7 over 25. So I'm going to go ahead and simplify it. Okay, now once you get the e to the negative 2x by itself, so we've isolated the e part of our equation, okay, we're ready to take the natural log now. This would be natural log e to the negative 2x equals natural log 7 over 25. And then we have, now the natural log e to the negative 2x is just negative 2x. Remember the natural log e, we're just going to drop, all right? And it's going to be equal to natural log 7 over 25. And dividing by negative 2, x is equal to natural log 7 over 25 divided by negative 2. Now if you have a calculator, you can put this up on your calculator. Now when I did it earlier, I got, let's see, so actually this should be over 20, I think, as we simplify here. So 35, 5 are going to 35 7 times, 5 are going to 20 to 100. Let's see, 20, let's see, over 100 here. So over 100, okay, this should be 20, not 25, so I just noticed that. So it should be 20, this will be 7 over 20. There we go, so these natural log 7 over 20 divided by negative 2. So just be careful with the fraction there as we simplify. So 5 will, just dividing both sides by 5, that'll give us 7 over 20. There you go. So let's do natural log 7 over 20 divided by negative 2. Now when I did it, I got 0.525, so 0.525. So when you take your answer out 3 decimal places and then round it off. Okay, let's do one more E equation, all right? So one more exponential equation. Okay, let's try this equation here. See number 3. Okay, this time let's take 5,000 over 1 plus, so we'll do 1 plus e to the 2x. Okay, equals 2. Okay, let's try this here. It has a fraction in it. Now we're going to start off as we got to get e to the 2x out of that fraction, so we have to isolate e to the 2x. So then we can take the natural log of both sides, and we can get the 2x out of that exponent. So let's start off. Let's multiply 1 plus e to the 2x to this side. And those two are going to cancel. Let's multiply 1 plus e to the 2x on the right. So this will be e to the 2x here. So multiply 1 plus e to the 2x to both sides, and we end up with 5,000 equals 2 times the quantity 1 plus e to the 2x. Now you can multiply 2 inside your parentheses if you want to. Now I'm going to go ahead and divide both sides by 2. So the 2's will cancel out here, and that'll give us 2,500 now equals 1 plus e to the 2x. Now subtract 1 from both sides, will give us 2,499 equals e to the 2x. All right. So you got to isolate e to the 2x power, and once you get that exponential term isolated, now we can take the natural log of both sides. So this will be natural log 2,499 equals natural log e to the 2x. So our final answer here, let's see to finish this up, this will be natural log 2,499 equals 2x. And then last, we just have to divide by 2. So dividing by 2, okay, we end up with, now the answer that I got was 3.912. So about 3.912. So you can kind of check that calculation, make sure that's correct, but I think it is. All right, so we've done 3 E equations. Let's try 1 or 2 natural log equations. So let's try 1 or 2 of those. Now, in my classes, we looked at, we kind of reviewed this type of equation in a previous video, but still we want to look at a couple of them. Now I want you to remember, we have to remember how to solve these E equations with E and natural log. So let's try this problem here. So number 4. So number 4, let's try natural log 2x minus 3. Natural log quantity 2x minus 3 equals 5. So equals 5. So equals 5. Here we go. Right. Now, what I'm going to do, I guess an easy way to do this, if you have more than one natural log, you have to condense your equation. In this problem here, we only have the one natural log. Now, natural log is base e. Right? So I'm going to convert from log form to exponential form. So the base to your exponent, so e to the 5th power equals 2x minus 3. So to solve a natural log equation, that's basically all you're doing. You're converting from natural log form or log form to exponential form. So we e to the 5th power. Remember, a natural log is basically equal to your exponent. So it's a way of expressing an exponent, basically. The 2x minus 3 is what we call the answer part of the exponent. Okay, e to the 5th power equals the 2x minus 3. Now to solve this for x, add 3 to both sides because it's e to the 5th power plus 3 equals 2x. Divide by 2. And we end up with e to the 5th plus 3 divided by 2. Now if you have a calculator that has e on it, you can punch that calculation up. I got 75.707. And that would be, once again, that's an approximation. That's not really equal, so it's kind of an approximation. That's a log function or log equation. Now let's try another log equation. Let's try do one more equation, then we'll get into some derivatives. Okay, let's try this one right here. It's number 5. Okay, let's take natural log of the square root of, let's do x plus 3. Equals 1. Now once again, let's convert from log form to exponential form. You can see this is our base, so base e. This will be e to the 1st power equals the square root of x plus 3. All right. Now all we have to do now is solve for x. So to get rid of your square root, let's square this side. And we've got to square this side here. So it gives us e squared equals x plus 3. Okay. And to finish solving for x, this will be e squared minus 3 equals x. And x will be approximately e squared minus 3. Now when I did it, I got 4.389. So about 4.389 They're fairly easy to solve. Now keep in mind, if you have more than one log in your equation, you have to condense your equation using your properties of logarithms. We've done a couple of problems. You know, this year is pre-calculus. There's no calculus here so far. But we want to get in some calculus right now. All right. So let's take a look at derivatives of E. Derivatives of E. All right. Now first, let me just mention, I played a little softball earlier. So I brought, or a little baseball rather. So throwing some baseball. I brought my baseball glove with me today. So maybe after I get down here today, I'm going to throw some passes. So get that out of the way. So let's get started. So let's see now. First of all, derivatives of the natural logarithmic functions. So derivatives. So derivatives of natural exponential functions. So natural exponential functions. Function. Right. And here we go. Right, so derivatives of E functions. How to find the derivative. So that's going to be two parts. The first part, get the derivative of e to the x. And let's see, part two here, we do derivatives of e to the u. Needless to say, when you take the derivatives of, when you work with these E functions and taking the derivative of E functions or E equations, there's a lot of U substitution you got to do. That's a lot of U substitution. So here goes. The derivative of e to the x is itself e to the x. So there you go. Makes it really simple. The derivative of e to the x is e to the x. And as far as I know, that is the only function in all of mathematics that is its own derivative. So the derivative of e to the x is itself e to the x. Now the derivative of e to the u is e to the u times the derivative of u, so times du. And this is by the chain rule. Now, so this is by the chain rule. So the derivative of e to the u is e to the u times e to the u. So if your function is anything other than e to the x, anything other than x for your exponent, you have to use u substitution. So a lot of u substitution we have to use as we get our derivatives on some of these. So this is it. So the derivative of e to x is e to the x, and the derivative of e to the u is e to the u times u prime. So times the derivative of u. Now, a couple things to notice here as we get started. All right, so we just kind of touch on this. Okay, let's take this function right here, because we see these a lot as we work with some of these equations. So if we kind of do these in our head, it'll kind of make some of these problems go a little bit faster. So let's take a look at this equation here. Y equals e to the negative x. All right, so let's start off with this one. So y equals e to the negative x. Now, when you take the first derivative, will be, as you take the derivative of e to the negative x, you've got to use this right here. This will be e to the negative x times the derivative of negative x. Or you end up with e to the negative x. Now the derivative of negative x is negative 1. So this is negative e to the negative x power. So when you take the derivative of e to the negative x, now once again you're using the chain rule, this will be e to the negative x times negative x. And the derivative of negative x is negative 1. This will be negative e to the negative x power. So this is negative e to the negative x power. Now, look at the second derivative. So what if we need to get the second derivative of e to the negative x? Now, the first derivative is negative e to the negative x. So the second derivative, so let's take a look at the second derivative. I said y prime is equal to negative e to the negative x. So when you take your derivative, the second derivative will be negative e to the negative x times negative 1. And the negative and a negative gives us e to the negative x. So the second derivative here is e to the negative x. Now, what about the third derivative? Okay, the third derivative is equal to, you can kind of see a pattern. Positive e to the negative x is the original function. The first derivative is negative e to the negative x. The second derivative, positive e to the negative x. So what happens? When you take the second derivative, I'm sorry, the third derivative. So the third derivative would be equal to, now take the derivative of e to the negative x again, we're back here, this would be e to the negative x times negative 1, which is negative e to the negative x. So the third derivative would be negative e to the negative x. So notice what happens now. You see the pattern. Start off e to the negative x. The first derivative is negative e to the negative x, then positive e to the negative x, and then negative. So the sign just simply changes with each derivative. So if you're looking for the fourth derivative, 1, 2, 3, 4, that would be positive e to the negative x. Right? Now, this is the one we use a lot. So we'll take the derivative of e to the negative x is negative e to the negative x. So you need to remember that. That's so we kind of once you know that derivative, we don't have to keep doing this process over and over again. So let's try a couple of problems. Now, so let's see if we can find the derivative of a few of these. All right. So let's see. Well, let's try. We'll start off with an easy one first. Let's try y equals 2 to the x minus 1. All right, so let's see if we can find the derivative on this one. The derivative. All right, now we've got several examples that we're going to look at here. We're going to run through a bunch of them. So let's start off with a real simple one here. Let's take y equals, let's see, y equals to e to the 2x minus 1 power. Okay, this is e here, so e to the 2x minus 1. Okay. Now, remember our property now, right? This is not just e to the x, this is e to the 2x minus 1. So we're kind of using the chain rule as we find this derivative, right? So the first derivative would be e to the 2x minus 1, right? So times the derivative of e to the 2x minus 1. So this will be our first derivative. So let's take the derivative of 2x minus 1 now. So we end up here with our first derivative is e to the 2x minus 1. The derivative of 2x is 2. The derivative of 1 is 0, so we end up with 2e to the 2x minus 1 for your exponent. That's our first derivative. Right? So once again, it's basically the e to the u times the derivative of e to the u. All right? Let's try another problem. Let's try this one here. So number 2. Okay, this time let's take f of x is equal to e to the negative 3 over x. We'll try this one. So f of x equals negative 3 to the x. And once again, we're just finding some derivatives, just doing some examples of some derivatives. Now, as we get our derivative, I'm just looking for the first derivative here. This will be e to the negative 3 over x times the derivative of negative 3 over x. Now, when you look at the derivative of negative 3 over x, so look at this derivative, all right? Negative 3 over x is the same thing as negative 3 times 1 over x, all right? And then 1 over x is the same thing as negative 3x to the negative 1. So as you get that derivative, we want to rewrite this, right? And then taking the derivative of negative 1 times negative 3 gives us positive 3. You got to subtract 1 from your exponent to the negative 2 power. So as you find your derivative now, this is it. So the derivative of negative 3 over x. You want to rewrite this as negative 3x to the negative 1 power, and then just use your power rule for derivatives. And this is equal to 2 over x to the positive 2. I'm sorry, 3. 3 over x to the second power. Right, so 3 over x squared. So as you look at our derivative now, this becomes e to the negative 3 over x times 3 over x squared. Now, if you want to, you can rewrite this. You can multiply these together here. This would be 3e to the negative 3 over x squared. So we can multiply those together, and the x squared will end up on the bottom of your fraction here. All right, let's try another one. All right, let's see. This is our second. Let's see. Let's try this problem right here. Let's try one. Those are pretty easy. Let's try one involving the product rule. Let's try this here. So number 3. So once again, we're just getting the derivative. Let's try f of x is equal to. Okay, let's do x squared e to the negative x. So x squared e to the negative x. All right, let's try this problem here. Erase this one. All right. Now, first thing you want to notice, this right here is a product. Okay, this is a product. get the x squared times e to the negative x. X squared is your first factor. E to the negative x is the second factor, so to find the derivative now, we have to use the product rule. All right, so to get this derivative, so we have to use the product rule. So as we set this up, our first derivative here, okay, this would be the first term times the derivative second, which would be, so x squared times the derivative of e to the negative x, so the first time derivative second, plus the second e to the negative x times the derivative of the first, or x squared. So the first time derivative second plus the second times the derivative of the first. Now remember, when you take the derivative of e to the negative x, and I just told you to remember that, all right? When you take the derivative of e to the negative x, okay, this will be e to the negative x times negative 1, or negative e to the negative x. So when you take the derivative of e to the negative x, you end up with all you do is change the sign on the front of it here. So when you take this derivative, then this will be x squared times negative e to the negative x plus, let's see, e to the negative x times 2x. So there's your derivative right there. And maybe I'll simplify it a little bit. This will be negative x squared e to the negative x plus 2x e to the negative x. So there you go. Erase that. Okay, so this is our derivative. Now the only other thing we may want to do maybe is, you can't put this in factored form. You notice you have e to the negative x in both of these. Also you have x, you have the same variable in both. So we can't put this in factored form. So it could look like this. Let's see, you got x squared and x, so it would be x, we factor off x, and then x e to the negative x here. Let's see what we have left when we factor this off. Now I'm going to put the positive one first. So you take x e to the negative x off this term here, gives you 2. This was negative, so it'll be minus. You're left with an extra x, so inside our parentheses it'll be 2 minus x. So you've got to put it in factored form. This is what it would look like, right? So if you had to find critical numbers or something like this, you'd have to set both of these equal to 0 and then solve for x. All right, let's try another example. This is the product rule. All right? Let's take this problem right here. Erase this. All right, so the product rule. Okay, let's see. How about see if we problem number 4, I believe. That's our fourth example. Let's take y equals, and this time we'll do e to the x plus 1 divided by or over e to the x minus 1. How would we find the derivative of this function now? Now, first thing you recognize, this is a fraction. It's not a natural log either, so you can't just expand it and then take the derivative, all right? So it'd be nice if we could, but I'm going to use the quotient rule here, all right? So we find the derivative here. All right, so you look at this function here, this is a quotient. So we have to use the quotient rule to find our derivative here. So we've got to use the quotient rule. So now we all know the quotient rule. We looked at this last semester. So let's see what our derivative here will look like now. So y prime will be equal to, so you take the bottom squared, so e to the x minus 1 squared. Then you start off with the bottom. This is e to the x minus 1 times the derivative of the top. Now the derivative of e to the x is e to the x. The derivative of 1 is 0. So the derivative of the top is e to the x. Minus, so the bottom times the top minus the top, which is e to the x plus 1, times the derivative of the bottom. Now the derivative of e to the x is e to the x. And the derivative of negative 1 is 0. So there you go. This is our derivative now. And now we, the fun part is going to be simplifying. And anytime you use the quotient rule, you're going to end up with this big fraction, then we got to simplify it. So let's see what our derivative here looks like. So this would be e to the x minus 1 on the bottom, quantity squared. And you got to multiply e to the x inside your parentheses. Now remember, when you multiply e to the x times e to the x, let me show us that. So e to the x times e to the x will give us e to the x plus x, or e to the 2x. So remember, when you multiply factors with the same base, you add your exponents. So e to the x times e to the x is e to the 2x. Now e to the negative 1 is negative e to the x. Now you got to watch out. So you always be careful with the quotient rule. That minus sign right here has to be distributed inside your parentheses along with the e to the x. So you're distributing the minus and e to the x. So e to the x times e to the x is positive e to the x, and then that negative is going to make it a minus e to the 2x, I'm sorry. So let me erase that. So it'll be e to the 2x. And e to the x times 1 will be negative e to the x. All right. Now, we removed our parentheses. All we have to do now is to combine like terms and then see if we can do anything from there. Now, looking for like terms, let's see. First of all, these two right here add up to 0, so those are gone. Now we have negative e to the x and negative e to the x. Those are negative 2e to the x on top. So the 2e to the x's we can add together, and this is going to leave us with e to the x minus 1 quantity squared. That's our derivative now in the simplest form. Okay. So that wasn't too bad. So just y equals e to the x plus 1, e to the x minus 1. All right. Let's try something like this problem again. But I'll tell you what, let's make it a natural log function now. So let's try a natural log. How would that look if it were a natural log? Yeah, so this one didn't have natural log in it. This is just a quotient. And what if we had, let me erase this. Okay, this would be problem number 5. Let's see, what if we had y equals the natural log now of e to the x plus 1 over e to the x minus 1. So what is this for a natural log with e in the answer part of your natural log? All right. Now, if you remember now, to find the derivative of a natural log u, so to find the derivative of natural log will be u prime over u. So you're going to get a fraction. But first thing I notice here, this here is already a fraction. So before we can take the derivative, we have to expand the natural log. So this becomes y equals natural log e to the x plus 1. Now this is a division, so when you expand it, you're using the quotient property of logarithms. So minus the natural log of e to the x minus 1. So as you expand it, this is what we get. Now we're ready to apply our natural log property for derivatives. Okay, so this becomes, so we got it expanded, so y prime, so we're ready to take our derivative now. And this will become e to the x plus 1. And the derivative of e to the x is e to the x. So on top will be e to the x minus, and this will be e to the x minus 1. And now the derivative of e to the x minus 1 is e to the x. And there you go. Now, I'm not going to combine these. I'm just going to leave them as the two separate fractions there, but that's how that will work. So if it's a natural log, if it's a fraction like this, you're going to have to expand it, and then you can take the derivative of it. Actually, a little bit easier than using the quotient rule, actually, I guess. So if it's a natural log, it wasn't that difficult. Okay, let's try this derivative here. So let's try something a little bit different. Okay, what if we have, erase this. This will be example number 6. Okay, what if we have capital F of x equals the integral from 0 to e to the 2x natural log quantity t plus 1 dt. So what if we have this type of problem now? Okay, we've looked at these integral functions, all right? So this is, we saw these when we looked at the fundamental theorem of calculus now. Now, to take the derivative now, so we find f prime. Now, as you get when you take the derivative of an integral, now you're using the second fundamental theorem of calculus here. So this will be the fundamental theorem of calculus, fundamental theorem of calculus, theorem of calculus number 2. We're taking the second part of the fundamental theorem of calculus as we get this derivative. So all we do, you take your exponent, plug it in for t. So this becomes natural log of e to the 2x plus 1. Then you got times e to the 2x. So the derivative of e to the 2x. So as you take that derivative, that's all you do. All right, so a big integral function, all right? And as you take the derivative, remember the integration and differentiation are inverses, so all we have to do is, we're just kind of using the chain rule here, substitute in times the derivative e to the 2x. So our derivative now becomes f prime x is equal to natural log e to the 2x plus 1. So natural log e to the 2x plus 1. So plus 1 times, now the derivative of e to the 2x. Now you take the derivative of e to the 2x, so e to the 2x would be, as you take your derivative, would be e to the 2x times 2, which is 2e to the 2x, right? So you got to use the chain rule there to take that derivative, I guess. And so simplifying this will be 2e to the 2x natural log e to the 2x plus 1. So this is our derivative now. So you got to use the fundamental theorem of calculus, part 2, to find the derivative of this integral function. So all you do is substitute the upper bound in. The upper bound has to be your variable. If it's not, then you've got to flip it and take the opposite, right? So you just have to substitute it in times the derivative of e to the 2x, and that's our derivative now. Okay, let's take another. So just a little something different there. Okay. Now you notice now some of these problems are getting a little bit harder and harder, right? It was the same property though. So let's try this here. Let's see if we can find, use the derivative to get the slope of a tangent line at a particular point. Let's see if we can do that. Let's see if we get the slope of a function at a particular point. So, okay, number 7 here. Let's see if we can find the slope of a tangent line. Tangent to the point, now what is the point 2, 1? And we'll try this function right here. We'll do y equals, let's see, let's try y equals e to the negative 2x plus x squared. Okay, let's try this problem here. Now remember, the derivative is slope. Right, so we got to get our derivative, and then we can plug in, we're going to plug our x value in, and that will give us our slope. Now, to get your slope, you have to be able to find the derivative of this e function, this exponential function. So, as we said, find our derivative now. Y prime will be equal to, this will be e to the negative 2x plus x squared times the derivative of e to the, times the derivative of negative 2x plus x squared. Now, I'm going to save me a step. I'm going to go ahead and take the derivative right now. Right? So, feel free to do so yourself. The derivative of negative 2x is negative 2, and the derivative of x squared is 2x. So that's our derivative here. And let's see, I'm going to move this to the front, so our derivative is so negative 2x, negative 2 plus 2x. So negative 2 plus 2x e to the negative 2x plus x squared. So that's our exponent, right? You know, this is our derivative. Now, to get our slope, all we got to do is substitute in now. So let's get our slope. Okay. So substituting 2 in for x will give us, what do we get? So it'll be negative 2, so negative 2 plus 2 times 2. Okay. E to the negative 2x for exponents will be negative 2 times 2. Okay. Plus 2 squared. Okay, that's going to give us our slope. Now, inside our parentheses, first will give us what? Negative 2 plus 4. E to the, now negative 2 times 2 is negative 4 plus 2 squared is 4. So our exponent is negative 4 to the 4th power, so we end up here with 2 e to the 0 power. And I'm sure you remember anything to the 0 power is 1. Right? So here we have 2 times 1. Or just 2. So this is our slope. Okay, so that's how you find the slope of your tangent line at a particular point on your curve. Once again, get your derivative, substitute it in. All right. Well, that was so much fun. Let's see if we can actually write the equation of a tangent line now. So let's see if we can try that type of problem. All right, so we just found the slope. So let's see if we can write the equation of our tangent line. Erase this. Yeah, so let's see, this will be problem number 8. Yeah, so we're kind of going kind of fast. Let's see if we can find the equation of the tangent line at the equation of the tangent line my students, when they get their homework on this section, there'll be several problems. They'll have to find the slope, or they'll have to actually write the equation of the tangent line. So they pay close attention here, because we're going to do one pretty good problem. Let's try this here. So do y equals x e to the x minus e to the x. Now, so we'll try this problem right here. Okay, at the point 1, 0. So just double check. Make sure I got it copied down correctly. So x e to the x minus e to the x at the point 1, 0. So what would the equation of our tangent line be? Well, there are two things you got to know. You got to know your point. You have 1 point on your curve, and we've got that. So that's the point 1, 0. And we need our slope. Now, for the slope, we have to get our derivative. So let's find the derivative of our function first. So y prime is going to be equal to. Now, when you take the derivative of x e to the x, that's a product. So we have to use the product rule. All right, so as we set this up, so it'll be the first times the derivative of the second. Now, the derivative of e to the x is e to the x. So the first derivative of the second plus the second e to the x times the derivative of the first, which is 1. So the derivative of x is 1. So that's going to be the derivative of our first term. So first derivative of the second plus the second times the derivative of the first. Minus, now the derivative of e to the x, that's easy, e to the x. So minus e to the x again. So this is our derivative now. Okay. Now let me simplify this a little bit here. So y prime is equal to the x e to the x, okay, plus e to the x minus e to the x. Okay. Right. Now let's see, we got 1 point, now we got to get our slope. So let's get our slope next. This will be at x equal, we'll substitute 1 in for x. So at x equal 1, right? So substitute 1 in for x, and see what we get now. This will be 1 e to the first power plus e to the first power, e to the first power, minus e to the first power. So what do we have here now? We got e plus e minus e. These cancel out. And the slope is e. Okay, that's our slope. Now let's go ahead and write the equation of our tangent line. Now I'm going to write mine first here, y equals mx plus b form. So write this in slope-intercept form. So this will be 0 equals e times 1 plus b. So substituting 0 in for y, 1 in for x. So we have 0 equals e plus b, or negative e equals b. So as we write our equation now, this should be, now the slope was e, right? So it'll be y equals e to the x minus e. So there you go. Now if you got a calculator, you put e in decimal form, but I'm just going to leave it like that. So it'll be e to the x minus e. Students that are taking taking AP Calculus, you guys may see this type of problem on a non-calculator question on the AP Calculus exam at the end of the year. So it'll be this type of problem. They're going to expect you to be able to work with these e expressions and e functions. Okay, so this is an equation of our tangent line. I said it wasn't too bad. Okay, well let's take it a step further. Rather than just writing the equation this time, let's see if we can find minimum or maximum. So let's see if we can find the relative extrema of a particular function. So let's try that. So how do we go about finding minimum or maximum? Erase this. So let's be number 9. We're going to find any relative extrema. It is maximum or min. So maximum minimums. Right, so let's take, let's see, this is on an open interval, so there's no endpoints to worry about. So let's try this function. We'll do f of x equals. Right, now all of these examples are actually, most of them pretty much are in our textbook. So you can find these, I'm sure, somewhere in our textbook. I'm just picking out some pretty good problems to look at. Okay, let's try this function here. This will be 2x. Okay, e to the 2x. Okay, so let's take a look at this particular function, and let's see if this would have any relative extremas. Would it have any max or minimum? So So to start off, let's get our derivative. Now to get our derivative, we have to use as you look at our function, now this is 2x times e to the 2x. We got to use our product rule. So you got to recognize for most students now with the product rule, if you're not really watching for it, you'll miss it, right? So you got to, you have to recognize that this is a linear function times an e function. So this is a product of two different functions, and you have to use the product rule. So to get our derivative then, okay, this will be the first, so it'll be 2x times the derivative of so the first time derivative, second, now the derivative of e to the 2x. So you take the derivative of e to the 2x, would be e to the 2x times 2, or 2e to the 2x. So you take the derivative, so the first times the derivative of the second, which is 2e to the 2x, plus, so remember the product rule is always addition, all right, so plus, so the first to the second plus the second, which is e to the 2x times the derivative of the first, which is 2. All right, so this is our derivative. Erase that. Now let's see if we can simplify it a little bit now. So our derivative, so 2 times 2 gives us 4x e to the 2x, okay, plus 2e to the 2x. All right. Now let's see, first thing I noticed now, we've got, so we're going to get our any, now there's a couple ways to get any relative minimum or maximum. So two tests, where we can use the first derivative test or the second derivative test. All right. Now, I only use the second derivative test if it's really, really easy to get the second derivative. Now, this is the first derivative, which wasn't that hard, but still, I don't know if I would want to try to get the second derivative unless I had to. Now, so I'm going to use the first derivative test here, right? So to get the any relative max or minimum. So we erase this. So we'll use the first derivative test. So the first derivative test. Find our max or minimum points. All right. Now to get to use the first derivative test, we have to find our critical numbers. Got to find our critical numbers. All right. Now critical numbers are where the first derivative is equal to 0, and where the first derivative does not exist. So the first derivative is equal to 0, and where the first derivative doesn't exist. Now looking at the derivative here, there's no fractions. Okay, this is an e. This is an e function really when you look at the first derivative. So there are no places where the derivative does not exist. Now, so it's going to be continuous everywhere. So no places where it doesn't exist. But we should be able to find some zeros here. So let's see, we have 0 equals 4x e to the 2x plus 2 e to the 2x. So set the derivative equal to 0, and let's see if we can find any derivatives there, or any zeros of the derivative rather. All right. Now remember, to find any zeros of the derivative, you got to put this in factored form. So we have to factor this. Right, so we have to factor this, and then we'll look for any zeros. So we have 0 equals. Now notice 2 and 4, you have a common factor of 2, and you have e to the 2x in both terms. So I'm going to factor 2 e to the 2x off. Let's see what we have left when we factor 2 e to the 2x off. Now, you take the 2 off the 4 gives us 2x. The e to the 2x is gone, plus factoring 2 e to the 2x off the second term gives us plus 1. So there you got it. All right, so let's see. We've got 2 e to the 2x equals 0, and 2x plus 1 equals 0. So let's see right away here we have 2x equal negative 1. X equal negative 1/2. So that's our first critical number, x equal negative 1/2. Possible, maximum, or minimum. Now we have to actually use the first derivative test to tell which. All right, so whether it's a max or minimum. Now solving this one, let me bring this one over here. This is 2 e to the 2x equals 0. So I'll solve this one over here. Now dividing both sides by 2, e to the 2x equals 0. Now to get x out of that exponent, remember you have to take the natural log of both sides. So I'm going to do natural log e to the 2x equals natural log 0. And now we got a big problem. Natural log 0 is not in the domain. Right? So this is not in the domain of natural log. So not in the domain, so there's no solution to this equation. So natural log 0 does not exist, so it's not in our domain. So this one, cross that out, we only have one critical number, and that's at x equal -1/2. So only one critical number. So now let me erase this. Now if you remember the first derivative test, easy way to do the first derivative test is fix up a little wiggle graph, we call it. All right, remember the wiggle graph? We looked at these last semester. Let's put the -1/2 right here in the middle. Okay, let's describe the derivative here and the function down below. So this is the derivative. Now remember, that first derivative tells you if the graph of the original function is increasing or decreasing. All right, so we got to pick us out a test value. So let's try maybe. Let's see. Let's try -1 and 0. So let's try these two numbers here. Let's see whether or not whether they're negative or positive. Remember now, with the first derivative test, when you substitute these into the derivative, the actual number doesn't matter. All that matters is whether the number is negative or positive. If it's negative, then the graph will be increasing. If it's positive, the graph will be increasing. Negative, it'll be decreasing. So let's try the -1. We'll substitute it into our derivative here. So we'll do f prime at -1 would be 4 times -1 e to the 2 times -1. So -1. Plus 2e to the 2 times -1. So substitute -1 in for x, and let's see if we can simplify this now. This becomes -4 e to the -2 power plus 2 e to the -2 power. Well, we can combine these. E to the -2 and e to the -2 should give us -2 e to the -2 power. Right, now since the 2 is negative here, right, this is going to be negative. Now you can punch it up on your calculator if you want to, but you shouldn't need to. It's going to be negative. You have a negative times a positive here, which would be negative. So this would be negative here. So our derivative is negative. That means the function itself is going to be decreasing. So from -infinity to -1, the graph will be decreasing. Okay, let's try 0 now. Substituting 0 into our first derivative, so the derivative is 0, will it be? So 4 times 0. E to the 2 times 0 power plus 2 times e to the 2 times 0. So let's see what we get here. Now this will be 4. Actually, this will be 0 here, right? So that'll be all be 0. Okay, plus 2 times e to the 0 power. Okay, which would be 0 plus 2 times 1, or just 2. Now, once again, this is a positive number. So that means the derivative is positive and the graph is now increasing. Right, so we use our first derivative test. Now notice we've got, erase this now. And let me see, I can erase this here too. So we used our first derivative test. So let's see, now if you look at your graph, the graph is going to be decreasing to the left of your critical number, then it starts to increase. So you're looking at a relative minimum. So a relative minimum. So this is our first derivative test. So about a relative minimum at x equal -1/2. All right, so x equal -1/2. Okay, so that wasn't too bad. So that's our relative, just a relative minimum. All right, so x equal -1/2. I'm just going to find the x value. You can actually substitute in to get the actual point. But we'll go ahead and move on a little bit. There's one more problem we want to look at. So one more. Now, this is finding using the first derivative test. Now, my students, when you get your homework, there'll be a couple of problems I ask you to find the relative minimum. So you got to be careful. You got to factor your derivative, look for your zeros or where the derivative doesn't exist. So one last problem. This will be number 10, and that's going to finish this up. So number 10, let's do one involving implicit differentiation. Let's try a problem involving implicit differentiation. All right. So let's try one of these. Let's do e to the xy for our exponent, okay, plus x squared.